Greetings, guys. I'll share the video.
Evening, Siyabonga. You can go ahead. Siyabonga, I think we only have 1 hour for this session. So I think what we can do is I'll go ahead and start the session now, and then at the end you can play the promotion video and the students can get the information from there. Is that fine?
All right, let me make you a host now, co-host now. Thanks.
Okay, thank you. I'll just wait about 2 extra minutes for the students who come in late. So I'll start 2 minutes past the hour. Thank you.
All right.
Good afternoon, sir.
Good afternoon.
I just want to ask a question. I matriculated in 2019, but I applied to rewrite for 2023 my maths and physics. So I bought a textbook, and it says here in the textbook that from 2021 chemical systems won't be examined. Is that still the case?
Chemical systems. No, I'm not aware of any changes. Nyameka and Sia, are you aware of anything?
I'm not aware
Okay.
of anything at the moment.
Okay. What we can do is take my you'll take my email address down,
Okay.
and get hold of me after the session, and we can discuss in detail, so that I know exactly what you're talking about. Okay.
Okay. Please, could you mention your email address?
Yeah, I'll drop it in the email just now. Thank you.
Okay, no problem. Thanks.
Okay. Okay, then let's get started. We have 13 people in the chat. Okay, my name is Mr. Ashwin Manival, and I'm one of the teachers at UKZN in the Chemistry Access Program, and I'm joined with Ms. Nyameka Diko, who's going to be assisting me on the chat and also answering chemistry questions. And our administrator today is Siyabonga Mbambo. And first of all, can everybody hear me clearly? Can everybody see my PowerPoint slide? Nyameka?
Yes.
Yes, we can.
Okay, thank you. Yeah, so today I only have an hour, so there's not much time. So what I'm going to do is I'm just going to put on the screen all the different sections I'm going to try and touch on today. I'm going to, well, these are concepts that when you're doing chemical equilibrium, these are concepts that you have to understand, right? Chemical equilibrium is an extremely important part of chemistry and science as a whole. When you come to university, you learn more about it. But what I'm going to do is I'm going to dive straight into this this topic today, and we're going to get started. After this, I'll do 2 or 3 examples, and then I want to go over some graphs of concentration and rates. So the first thing we have to talk about is something called a dynamic equilibrium. And so when you, let's just take a hypothetical example of a reaction that happens in solution. You normally will see something like this. You'll see some reactants on the left, and you'll see a double arrow, and then you'll see some products on the right. And this is the simplest case of that sort of scenario. It's a hypothetical example. So this double arrow, what this means is that there's an equilibrium that has been established. Both arrows face in opposite directions and the equal length. And so what this means is that when the equilibrium is established, what it means is the rate of the forward reaction is equal to the rate of the reverse reaction. So there is a dynamic equilibrium that is set up. Now, if you had to come on a very superficial level, we call on the bulk scale, if you had to look at the bulk properties of the matter, you won't see any change in the products or reactants. You won't see any change in their concentrations, okay? And because concentration is a bulk property of the solution that you're looking at. And what you have to understand that on the microscopic level, there are still molecules of A, for example, being changed into B, and molecules of B that are being changed into A. And this process continually happens in such a way that you do not notice any change in the concentration. The concentrations look constant. They're not equal, they're constant, but the rates of the forward and the reverse reaction are equal at the equilibrium. And so we call it dynamic because there's constant movement on the microscopic scale, but on the macroscopic scale, you don't see anything. There is a process called reversible reaction or reversible process when we talk about equilibrium. If I had to illustrate this point to you, if I took a piece of wood like this, a piece of plank, and I rested it on a pivot, right, on a pivot point. If this piece of wood is perfectly balanced in the middle, we say it's at equilibrium, we say it's at a mechanical equilibrium. Now, a reversible reaction, a reversible process is a process where the equilibrium can be shifted either way, either left or right, if an infinitesimal change is carried out in the system. Now, these are just fancy words, but what this means is if I took a grain of sand, if this was at perfect equilibrium, if I took a grain of sand and I put 1 grain of sand on this, it would tipple the scales this way and the plank would bend towards this direction. But it also means that if I do an infinitesimal change in the other direction, I put a small amount of sand again, or a grain of sand, it will tip back into the balanced equilibrium state. And so a reversible process is a process where you can shift the equilibrium with small changes. And later on, we'll talk about Le Chatelier's principle. We'll talk about how we shift equilibrium. Phase equilibriums are important in chemistry. And so, for example, I can give you an example of water. If you had H2O liquid, and this liquid sort of underwent a process where there was a transition into a vapor or a gas, right? This is the difference between vapor and gas, but we won't get into that now. So if you have an open container like this, the drive is in one direction. All of this liquid water will become evaporated and will escape the container. But if I put a lid on this container, if I closed it off like this, I allow some of the vapor to get trapped inside that flask. And so what happens is a dynamic equilibrium gets set up. I allow, by closing the system, I allow the system to establish equilibrium between its liquid and its vapor at a certain temperature. And so this is, again, boils on the idea of open system and closed systems. In fact, you will see one of the requirements for chemical equilibrium is that you need a closed container when you're dealing with gases, right? If you don't have a closed system, you can't establish equilibrium. The process needs to be reversible. If you're dealing with a solution, it must be homogeneous. But if you do have precipitate in that system, then the precipitate must be saturated. That compound must be saturated so that the precipitate is not sort of allowing another avenue through which concentration can change during the process, right? The equilibrium constants is something you would have studied. We're going to go over equilibrium constants just now. And there is a temperature dependence on equilibrium constants, right? So equilibrium constants are dependent on temperature. If you change the temperature, you change equilibrium constant. This is something you should learn in class. Calculating Kc, we're going to do a calculation just now, so I won't go too much into this. And of course, the Le Chatelier's principle has to do with changes. So you know that when a chemical system is at equilibrium, for example, if I increase the temperature of that system, remember Le Chatelier's principle says that when a system at equilibrium experiences a stress, that system will act in such a way as to counteract that stress, right? So if I have counteract the stress and return back to equilibrium. So if I have a chemical reaction and in a vessel and it's at a certain temperature and I increase the temperature, remember, if that chemical reaction is in equilibrium, then there'll be a forward reaction, there'll be a reverse reaction, and there'll be an endothermic and exothermic reaction. So this is just one example where if the temperature goes up, then the energy of that system, the thermal energy of that system goes up. So the system wants to use up thermal energy. The thermal energy is the stress. And so the system is going to try to relieve that stress by using up some energy. And the best way the chemical reaction knows how to use up the energy is to favor the endothermic process, which sucks up energy. So when you're doing these questions, I expect you to apply this kind of logic. We'll talk about pressure and catalyst and concentration just now. And then graphs we'll go through at the end really quickly. So let's get into an example. We're dealing with a question that I've taken from somewhere for us to do today. Let's change the color of this pen. Right, so we have a mixture of 6 mole H2 and 5 mole I2, and this is a sealed container. It's 500 centimeters cubed, so that's 500 milliliters, that's half a liter. And they tell us that the temperature is 460, and they've given us a chemical reaction right here, okay? And they say at equilibrium, 4 moles of this HI is present. So what they want us to do is they want us to calculate the concentration of H2 and I2 at equilibrium. So this is really simple. First, what you would do here, of course, is you have the equation. We're going to use something called an ICE table. So I say ICE table because it has the I, the C, the E, and that stands for initial, which we're going to measure in moles. It stands for change, which we're going to measure as moles. And this is equilibrium, which we're going to measure as moles. And the different species we have, of course, we have the H2, we have I2, and we have HI. I put them in order of the way they appear in this reaction. So they tell us that there's 6 moles H2, so that's the initial amount we'll put in the table. They tell us that there's 5 moles of I2. This is given in the question. And they say that those two are sealed in the container. So, of course, there's 0 HI at the beginning. So during the process of the change, we can see now that what's given to us is we are told that at equilibrium, there's 4 moles of HI present. Now we're going to use some stoichiometry here, and we're going to do some calculations. But we know that if there's 4 moles HI present, then during the change process, there had to have been 4 moles of HI that formed. Had to. The HI can only come from this reaction driving forward. At the beginning, there was no HI. So during the change, it must be plus 4 because they're telling us there's 4 present at the equilibrium. So the question is, if there's 4 HI present at equilibrium, how much H2 and I2 reacted in order to produce that 4? And so what we see now is we can use stoichiometry, and we can see it's 2. For every 2 HI that form, there's 1 I and there's 1 H2. Don't be confused by the subscript 2 and on the H and the subscript 2 on the I. Don't be confused by that. We're looking at the stoichiometric coefficients. The stoichiometric coefficients are the numbers that are in front of the species in the chemical equation. So here there's a 1. If you don't see a number, it's a 1. Here on this side, it's a 1 on the I2. And so the HI has a 2. And so logic will dictate that it's half. If 2 is to 1, then this is half. And the half of 4 is 2. And so minus 2 minus 2. To find out what's at equilibrium, we just take the difference. We take what was there initially for H2, which is 6, minus 2, and we end up with 4. For the I2, we say, okay, there was 5, minus 2, we end up with 3. And then at equilibrium for HI, we know there's 4 at equilibrium. And so then what we do is we want to calculate the concentration. I'm just going to put these brackets, concentration at equilibrium, and that's going to be in moles per decimeter cubed. And we're going to take the 4, divide by 0.5, because remember, it's a 500 centimeter cubed. So 500 centimeter cubed, right, is the same as 0.5 decimeter cubed, or 0.5 liters. This is the same as 500 milliliters. And we know that there is 1,000 milliliters in 1 decimeter cubed. And so to get to the decimeters, we divide by 1,000. And if we do that, we jump 1, 2, and there's a decimal there. We jump the decimal, and we end up with this, right? And so 3 over 0.5. Hope everybody understands why I'm using the 0.5 and the 4 over the 0.5. So this, remember, C is equal to N over V. So molar concentration, molarity, would be the number of moles, which we calculated using our table, divided by the volume. The reason why I use 0.5 for all of them is because they all are in the same container. Everybody's in the same container. So you use the same volume for the concentration calculation. And so at this point, we can see that we'll end up with numbers. The concentration here will be 8. The concentration here will be 6, and the concentration here will be 8. And those are the concentrations for those species. The question asks, calculate the concentration of H2I2 at equilibrium. These are your answers here, and your units on the side on this table. So that's how you get through the first question. The next one, the question is asked here, Kc calculated at 130 degrees Celsius. So this question is a little bit tricky, but it's asking, it's saying the Kc value, right, at 130 is 3. So I'm going to write it down. I'm going to say the Kc value at 130 degrees Celsius is 3,125. That's a given information. The question is the delta H for the reverse reaction positive or negative? Now you have to use some common sense and you have to use some logic here, right? Remember, equilibrium constant is dependent on temperature. It's dependent on temperature. And so if you look at our question, this whole problem, or this initial Kc that was given to us, the initial Kc that was the initial temperature of this process, well, the Kc wasn't given, but the temperature was 460. So you can see here 460. So what we have to do now is we have to try and figure out, okay, we know what 130 degrees is, and we know what the Kc is at 130 degrees. We were given 460 in the problem. Is there any way at 460 that I can calculate what the Kc would be? Right? So I'm going to say at 460 degrees Celsius, Kc would be, I'm going to draw an expression for Kc. This is important. Kc would be the concentration of Hi squared divided by, look at your equation, this is an H2. Remember, they're raised to the stoichiometric coefficients, right? I2. And so what we have is, remember, we have our concentrations from the table. We can go 8 squared. So let me just come back to the expression. If you look at the equation that we have, you can see that Hi is the product, so it goes on the top, and its stoichiometric coefficient is 2. And you can see that H2 and I2 are reactants, and they go at the bottom. And they also raised to their stoichiometric coefficient, which is 1, which I'm not showing there. Now, I'm going to plug in the concentrations that I used to calculate, and I get an answer of 1,33. So, we already know at 130 what the concentration is. We don't need to, or we already know what the equilibrium constant is. So we're going to draw a deduction now. Let me just quickly highlight here the important things. The first important thing is that 130, this is the Kc. The second important thing is that at 460, this is Kc. Now straight away we can see a trend here. We can see that as temperature, okay, as the temperature increases, the Kc value is decreasing. So when we have the higher temperature, we have the lower Kc value. When we have the lower temperature, we have the higher Kc value. So this tells us something. Since temperature favors the endothermic, remember, increase in temperature, if we increase the temperature, we favor the endothermic reaction, right? And remember, the more the reaction pushes forward, the higher the Kc. So if you have a lot of yield, if you have a lot of product, then Kc is going to increase. But in this problem, as we increase the temperature, it seems like the reverse process is being favored because the Kc is decreasing. So what this will lead us now to deduce is that since the increase in temperature favors the endothermic process, the reverse reaction must be endothermic. So the reverse reaction must be endothermic. I'm going to go over that one more time, this train of thought. I have two temperatures and I have two cases. Kc is an indication of how well the reaction goes forward. The reaction you see in your equation. Remember, Kc comes with an equation. That equation on top, the H2 plus I2 gives you 2HI. That equation and that Kc go together. So if the Kc is high, it means the reaction is going forward. But when we increase our temperature, we see Kc dropping. That means that with the increase in temperature, the reverse process is being favored. The backward reaction is being favored. So that must mean, because we know increase in temperature favors endothermic process, that must mean that the reverse reaction is endothermic. And if it's endothermic, the question is asking you, what is delta H for the reverse reaction? Then the delta H for the reverse reaction must be positive. And that's the answer for this question. Now, I don't have time to stop and take questions here, but the recording will be posted and you can go back and maybe we'll ask some questions at the end of the session if we have some time. So I'm going to go over to the next question. I see there's some chats here. Okay, so the next problem is number 2. This problem is asking us, it tells us that a solution of K2Cr2O4 in water gives the following equilibrium reaction, which takes place at 25 degrees Celsius. So again, a few evident things that they're showing us is that they're giving it to us at a specific temperature. There's a reason they're giving it to us at a certain temperature. Remember, equilibrium constants are temperature dependent, right? And so the reaction has 2Cr042 minus, which is yellow, reacting with some acid H plus, and this is an equilibrium with Cr2O72 minus, which is orange in color, and also H2O. Now, this H2O, it's important to note here that this H2O is a liquid. Hope you can see that. What this means when something is a liquid, it means that this substance that is liquid is actually the solvent. It's the solvent. Okay, remember the difference between a solvent and a solute. The solvent is in large quantity. The solvent is normally, you see all of these species have AQ. What the AQ means, AQ is telling us it's aqueous solution. It's telling us that the solvent in this process is water. All of these species are surrounded by water. And so for this reason, because the solvent is present in such large excess in a solution, its activity in the solution actually tends to unity. And so we don't include the liquid in the equilibrium constant calculation. We don't include solids. We only include species who have an activity in solution, right? You can only affect an equilibrium if you have an effective sort of chemical potential within the solution, but that has to do with the activity in the solution, right? Now, let's go on to the question itself. It says, give 2 ways of forcing the equilibrium to the right. So you want to manipulate this equilibrium. You want to get it to move towards the right. Well, the first way is you could add acid. You could have acid, right? You could add some acid. Because acids would increase H plus. It would increase H plus, and if you increase the H plus by adding the acid, you will drive the reaction to the right. So this, again, this is Le Chatelier's principle. If you introduce a stress to the system, if you increase the concentration of H plus in this equation, it will drive the equation to the right. And so that's one of the answers. The second one is you could add concentrated H2SO4. You could add concentrated H2SO4, which is a dehydrating agent, right? And that will remove water. If you remove water, it will drive the reaction, right? It will shift, it will cause shift. Number B, give one way of increasing CrO4 2- concentration. The one way you could increase the concentration on this side is to add an alkali. So you want to shift the reaction to the left. So this is the opposite question. You want to shift the reaction towards the reactants. You want more CrO4 2-. And so what you would do is you can add an alkali. So you could add an alkali, and what this alkali would do is that the alkali will react with H plus and it would reduce it. So if you add the base, it will react with the H plus, it will remove the H plus in solution, and then your reaction is going to try and compensate for that and make more H plus, and it's going to drive the reaction to the left. The third question, C, is asking us, what color change will take place if barium 2+ ions are added to the mixture and the precipitate barium CrO4 solid forms? So let's see. If you are pulling out CrO4 with barium, then you will get a change in the solution. What will the change in the solution be? In this process, you are pulling out which ion? Are you pulling out this one or are you pulling out that one? I'm going to leave this question for now. I'm going to come back to it just now. I'm going to do question D really quickly. So question D is asking us, write down the equation Kc for the reaction. So write down the equation Kc for this reaction. So let's draw the equilibrium constant for this reaction. When you look at this reaction, so you will have Cr2O72- on one side, raised to its stoichiometric coefficient, which is 1. We leave out the water, okay? So the water will not affect this because it's a liquid. And we have CrO4 2- squared. We include the H plus, and that's also squared because of the two coefficients here, right? So let's go back to this question. The question says, what color change will take place? So this is question C, will take place if barium 2+ ions are added to the mixture and the precipitate of barium CrO4 solid forms. What color change will take place? So in this case here, it says, well, the answers I have says orange will change to yellow. And the last question, E, the last question E here, which is what effect would it have on the Kc if more CrO4 2- is added to the reaction at 25 degrees Celsius? So what effect would, the question is basically asking you, would this equilibrium constant here, right? Would this equilibrium constant change if you were to add some of the reactant to the reaction mixture? So the answer here is that as long as your temperature remains the same. The temperature that was given in the problem is 25. The temperature that's given here in this addition is 25. The Kc will remain the same. This equation will shift its concentrations. It will shift towards the right. It will adjust its concentrations, but it will still establish the same Kc value. Okay, the Kc value in this process will not change because the temperature at which this is taking place will not be changing here. So I want to go back to this question one more time. This number 2C. So I just want to quickly check my source from what I got. This something is not looking right there. So I'd rather correct this with you while you're here. If you can just give me 1 minute for that. Right, so I'm going to say here that if your precipitate, right, if your precipitate that's being pulled out is barium CrO4 2-, if that's your precipitate and it's CrO4 2-, if your barium is pulling these guys out, if your barium is pulling that out of the solution and forming a solid, then what will happen, essentially what will happen here is you will have these left in solution, right? You will have these left in solution. But also what else will happen is that if this is left in solution, if there's another process that's pulling these ions out, forming the precipitate, then this reaction will shift in that direction. This reaction will shift in this direction, right? Because remember, the stress here is that you're pulling out CrO4 2-. You're pulling it out as a precipitate. So the reaction will shift in this direction and it will make the solution more yellow. So that answer seems to be consistent, right? So what we're going to do is we're going to close this problem up and we're going to go on to question number 3. I'm just going to check the chat to see if there's okay. So let's go on to the question 3 very quickly. So this question is saying to consider the following reaction in a 300 milliliter container. And so you've got PCl5, which is a gas in equilibrium with PCl3 gas and Cl2 gas. And so at equilibrium, they give us the concentrations. These are equilibrium concentrations, so they're being kind to us, but that's never a good sign. But the question is saying calculate the number of moles of each gas at the equilibrium, right? Calculate the number of moles of each gas at equilibrium. So we know that the container is 300 centimeters cubed, which would be 0.3 decimeters cubed, right? And so the number of moles of PCl5 would be equal to C times V, which would be, what are those moles of PCl5? It's 3 multiplied by 0.3, which would give me 0.9 moles. We also know that the number of moles of PCl3 would be equal to C times V, which is 0.5, because that's what was given to us, multiplied by 0.3, which would give us 0.15 moles. The number of moles of Cl2 again would be C times V, which is 0.5 times 0.3, and again that would give us 0.15 moles. You can see I use 0.3 for all my volumes because all of these gases are in the same container, right? And we know that C is equal to N over V. So if you want number of moles, you rearrange. If V is being in the denominator here, when you take it across, it goes on the top to the numerator, that's CV. The next question is calculate the equilibrium constant for this reaction. So that's B. And so the equilibrium constant again would be Kc. And so to draw up the expression, I look at my products over reactants. So I've got PCl3 and I've got Cl2. All of them are raised to 1 because all the stoichiometric coefficients is 1. And this is, of course, concentration PCl5. And so I take, what would I take here? This is the, well, it's not supposed to be tricky, but you don't take the moles, you take the concentrations, right? 0.5 times 0.5 divided by 3, and that would give us 0.083. So that's what your Kc value would be in this case. The next question is, when the temperature of the reaction is increased, the Kc value decreases. So when the temperature is increased, the Kc decreases. Predict whether the forward reaction will be endothermic or exothermic. So this is question C. And so as the temperature increases, we can see that the Kc value here is decreasing. Okay? Therefore, the reverse reaction is favored. The reverse reaction is favored for an increase in temperature. That must make sense there, right? If the temperature is increasing and the Kc is decreasing, it means that with an increase in temperature, the reaction is choosing to shift backwards and decrease your yield. So the reverse reaction is favored, and so the reverse reaction must be endothermic, and so the forward reaction must be exothermic. The reverse reaction must be endothermic. Therefore, the forward is exothermic. Right? And in question D, run out of space here, but let's see if we can finish it here. Question D, the question is asking, explain why referring to the Chatelier's principle, what will happen to the Cl2 concentration if the pressure on the system is increased by decreasing the volume, but the temperature remains constant, right? Now this is important that they told us that the temperature remains constant, because we're doing a change here, right? The change here is that we are decreasing volume. So if we decrease in the volume of the system, it means that at constant temperature, remember the system has three things, it has pressure, temperature, and volume. If we're going to change one of them, we must not play with the others. So when we decrease the volume in this case, and if we keep temperature constant, that means that we're going to increase the pressure. And so we know what Le Chatelier's principle says about the increase in the pressure. So if we increase the pressure by decreasing volume, the reaction will shift to the side with a smaller number of moles. Remember now how you view this. This is a container, right? This is a box, and it's got molecules, gas molecules in it. And what these gas molecules do is they move. They have thermal energy, they move. And when they move, what they can do, or what they do, is they hit the walls of the flask. They collide with the walls of the flask. And by colliding with the walls of the flask, they put a force on the walls of the flask, and thus they exert a pressure. That's the pressure. The pressure we're talking about is the pressure exerted by the gas on the walls of the flask. And so that pressure is dependent on a lot of things. It's dependent on temperature. If you increase the temperature, these particles are going to move faster. But remember, we didn't change the temperature. Temperature is constant. The other thing that affects it is the number of gas particles. If you have a large amount of gas particles, then more particles will hit the flask per unit time, and they'll increase the pressure. If you have fewer gas molecules will hit the flask per unit time, and you're at lower pressure. So if your strain on the system is an increase in pressure, this system is going to want to try and decrease the pressure. And the only way it knows how to do that is that it's going to shift to the side with the smaller number, the least number of moles. In this case, the reaction would shift in the reverse direction, because you can see on this side of my equation, if I combine those two, I have 2 gas molecules here. And on this side, I have 1 gas here. And so it's going to shift in the reverse direction. And so let us answer the question now. It says, explain by referring to Le Chatelier's principle what will happen to the Cl2 concentration. Obviously, the Cl2 concentration will decrease. Cl2 concentration will decrease because by increasing pressure, you want to go to the smaller number of moles, and you're going to shift in the reverse direction. And so that's how we work through and explain this problem. Now, the next topic I want to touch on, this is an important topic because it shows up in papers in different forms, in different ways, are graphs on concentration and rates. And what's important about this section about the graphs on these this sort of section is that you need to understand certain areas in these graphs, right? So we have a reaction here, and the reaction is a simple one. It's 3H2 plus N2 to give us 2NH3. They're all gases, and you can see they're telling us that delta H is less than 0. So if delta H is less than 0, then this process, the delta H is negative, and so it's exothermic, right? It gives off heat. It gives off heat during the movement in the forward direction. Now, on your chart, on your graph, you have concentration here on the y-axis. You have time on the x-axis, and then you have different sort of reactants and products that are shown. The concentrations are shown here. Now, what you have to understand here, time 0 represents when the reaction starts taking place. You can see there's no NH3 in the beginning because it's not there. There's maximum amounts of H2 and N2, and as time progresses, you can see H2 is dropping in that area. You can see N2 is dropping. You can see NH3 is increasing, right? And when they get to this point, T1, you can see that it's a straight line, as straight as I could draw it, okay? But it's a straight line, and what that means is the concentrations have looked like they stopped moving. They're constant. And we know that when the concentrations look constant, we've reached equilibrium. So what this, between T1 and T2, what that representing in all of these diagrams is equilibrium. Now, at T2, you're going to do something to affect that equilibrium. You're going to bring some change about. And the change we do in here is we increase in temperature. We are increasing temperature in this problem. If we increase temperature, we know increasing temperature favors endothermic process. The energy wants to use up, the reaction wants to use up this extra energy that you're putting in, this increase in thermal energy. The reaction wants to use it up, so it's going to favor the endothermic process. And so because this forward reaction is exothermic, what do you think is going to happen? The reaction is going to go in the opposite direction. It's going to go in the reverse direction. And that's exactly what you see. So when you look here at the H2, you can see how the H2 starts to increase. And you can see here how the N2 starts to increase. And you see how the NH3 starts to decrease. This is exactly what we would expect. Now let's go over to the rates. If you look at the rates, I drew the forward reaction in green. I drew the reverse reaction in red. You must always understand the students. When the reaction starts at the beginning, t is equal to 0, the forward reaction is always going to be faster than the reverse reaction, always, because the reaction is driving to equilibrium. The two reactions are driving to be equal. In the beginning, the reverse reaction will be very high. The rate will be very high. And so the forward reaction will be very high. The reverse reaction, the rate will be very low. But as time goes on, one will decrease, one will increase, and they'll come to equilibrium where they both equal at some middle point, right? And that represents the equilibrium here. If you look at T2, you will see that when T2 happens, at T2, as soon as we increase the temperature, there's a jump here, and that jump is on the rate of the reverse reaction. And so I got a note saying reverse reaction favored. You can see here the reverse reaction then drops out, and the forward reaction will come up slowly, and they pan out again to a new equilibrium. Similarly, if you have the decrease in the temperature, I'm not going to go over this because I've been through the temperature. The opposite would happen. You'd get an increase at T2 on the NH3, and you'd get a decrease on the N2 and the H2. And so in this process here, you have the forward reaction is favored. But what I will say is the reason why you get the dip towards the bottom, the reason why these are jumping to the bottom, is that when you decrease the temperature, remember, you decrease temperature, you will lower rate of reaction for both forward and the reverse. Because remember, rate of reaction is dependent on temperature. Whenever you increase temperature, you increase the number of collisions, you increase the rate. Whenever you decrease temperature, you decrease the number of collisions with your rate theory, and you decrease the rate. And so, but the whole point is that the reaction that's favored will always be towards the top, and that's how you'll identify it. And so what I'm going to do, I'm not going to go through every single one of these. I'm going to put these up on the screen. I'm going to browse through with an increase in pressure. This is the next one. What will happen if we increase the pressure? Again, when we increase the pressure in the system, you can see that there'll be changes in this in the system here, right? So straight away, you'll get, we'll be increasing the pressure on the system by decreasing the volume. In your Matric course, I think there is another way to increase pressure by inert gas, but we're not going to deal with that. I don't think you deal with that at school. But if you decrease the volume, remember, decreasing volume, concentration goes up instantaneously. So you can see all your gases are jumping. You see all of them have that initial bump. The reason they all have the initial bump because you decrease the volume, you increase the concentrations, but you also increase the pressure. And so what would you expect if you increase pressure? To go towards a smaller number of moles. Which way is a smaller number of moles? It's towards the right, because there's 2 gas moles here, and there's 4 gas moles on this side, 3 plus the 1. And so you begin to see the forward reaction, NH3 increases, N2 decreases, and the H2 decreases. And so you can see forward reaction is favored, and that's why you get the spike on the forward, and then you get the 2 rates coming together at the end. And so I'm not going to go intently on all of these, but that's how you look through and you interpret the pressure on these diagrams. Remember something, the higher rate, the one that is, when you have the 2 curves here, the higher curve will always be the one that's favored with the rate when you look at that. And so we have increase in concentration. Again, this one is self-explanatory. We are increasing the concentration of NH3, of course, so its concentration goes up here. And then you'll begin to see the reaction will want to get rid of NH3, and so it shifts it in the reverse direction, and NH3 decreases while your reactants go up. And so I'll just put these on screen again so you can pause the video when you look at it later on, so that you have some idea of what these curves are going to look like. But I'm not going to go through each one. That's how basically how you interpret the different areas on the curve. So the last one, the last problem I want to do, and I've got 10 minutes left, has to do with a question that's taken from a past exam paper. And so this is a real life example. real life training. It says pure hydrogen iodide gas, HI gas, of concentration 1 mole per decimeter cube is sealed in a 500 milliliter container at a temperature T. It says the reaction reaches equilibrium according to the following balanced equations. It gives you the equation. We've seen this equation before. Maybe it turned the other way around, but we've seen it before. And then the question asks, define the term chemical equilibrium. So I've written this answer out for you, anticipating that I wouldn't have time, but chemical equilibrium, two things you can mention when you're defining it, is the rate of the forward and the reverse reactions are equal, and the concentration of products and reactants are constant, right? And you'll get marks for those. The next question, 6.2, it says the graph shows how the concentration of reactants and products vary with time. And there you have a nice axis. You have time, the x-axis, you have concentration, and your y-axis. And then you have some x curve, which seems to be increasing. You have some y curve, which seems to be decreasing. You have some time, 4 minutes here, where they seem to intersect. And then you have 6 minutes here, where both these curves seem to flatten out. Both concentrations seem to be constant, they're not changing. And so that's indicative of us, because we know that when concentrations appear constant, we know that we've reached equilibrium. But let's see what the question's asking. The question's asking, 6.2.1, which one of the curves, x or y, represents the changes in the concentration of the products? Give a reason for your answer. Very easy question. Free marks, right? So which one represents the products? Now, initially, you won't have any product. You have to realize this. If the time is 0, it means you only have reactant. And so whichever curve is showing an increase must be your products. Whichever curve is showing decrease must be your reactants, right? And so the answer is X. This curve shows concentration increasing with time, products increase in concentration until equilibrium is reached where they remain constant, right? That's 6.2.1. 6.2.2, it's asking, how does the rate of the forward reaction compare to that of the reverse reaction at t is equal to 4 minutes? You must choose higher than, lower than, or equal to 4 minutes. Now, there are a lot of students who will look here. You see where these two, at 4 minutes, these two curves intersect. There are a lot of students who will look there and say, the rates are equal, right? That's wrong. That's wrong. That thinking is wrong. I want you to follow this understanding, right? In the beginning of your reaction, when time is equal to 0, the only thing you have is reactant. The only thing you have is HI. As the time begins to increase, you start to make some product. You start to make some product. You start to make product and you use up reactant. You make product, you use up reactant, until you reach equilibrium where the concentrations are constant. They're not the same, they're constant, right? Reactants are constant, products are constant concentrations. But what about the rates? What about the rates? At the beginning of your reaction, listen carefully to me, when time is equal to 0, the highest rate goes to the forward reaction, the highest rate, because it has a lot of concentrated reactants just ready to react, and so the rate of the forward reaction is high. At the beginning, the rate of the reverse reaction is low, because obviously now, remember, for the reverse reaction, your products are actually reactants for the reverse reaction. But there's none of them, so the rate is low. So what we have is this process where the rate of the forward reaction is very high in the beginning, and then as it goes on, it starts to decrease, and it will decrease. And the rate of the reverse reaction is very low at the beginning, and as it goes on, it begins to, what will happen to it? It begins to increase. So let me say it again. Maybe I made a mistake there, or maybe I said it a bit wrong. The forward reactions rate is very high at the start, and as it goes on, that rate will begin to decrease. The reverse reactions rate is very low at the start, but as it goes on, it will begin to increase. there will come a point where equilibrium is reached, where they're the same, right? But they are only ever the same at equilibrium, and we know that equilibrium is at 6. We know that equilibrium is at 6 because the concentrations become constant at 6. 4 is not equilibrium. 4 is before equilibrium. So before equilibrium, the rate of the forward reaction is always higher than the reverse. The rate of the reverse reaction, if you start at time 0, the rate of the reverse reaction can never be higher. When you reach equilibrium, it will be equal, right? And so the rate of the forward reaction in this case is higher. Don't be tricked by that one. The last question is one of the question where you'll have to do calculation. But the last question is asking you, it says the equilibrium constant Kc for the reaction, they give you the equilibrium constant 0.04 at a certain temperature, and they say calculate the number of moles of iodine present. And so what you will do in this question is you will have to draw your expression, right? So you know how to draw your expression. Now you've got H2 and I2 on this end, they go to the top, and then you've got HI, and you use a 2 at the top because there's 2 on the stoichiometric coefficient here. You have to use an ICE table, so initial change, equilibrium, and concentration. And so your aim is to figure out what the initial moles of HI are. You've been given a concentration, you've been given a volume, so you can calculate the initial moles. And so you know the initial moles of HI is 0.5, and you know that these guys are 0. So to change, we're going to apply this X. We're going to say let the mole of I2 formed equal X. And if I2 formed is X, then from our equation, the same amount of H2 must form because it's 1:1. See, stoichiometric coefficient is 1, stoichiometric coefficient on I2 is 1. So it's 1:1. If you look at HI, you can see there's a 2. So twice as much must be used. So this is -2, HI is -2x. So HI is -2x, H2 is x, and I2 is x. And then what we do is we draw an expression for the concentration, which is 0.5 minus 2, because that would be the number of moles at the equilibrium, right? So in this case here, I think I left something out here, but so this would be 0.5 minus 2x, right? That would be the moles. This one would be x, and that one would be x. And let me make this clear by drawing a line. That's different, okay? So at equilibrium, that's what you'll have. And when you come down to your Kc expression at the bottom, you'll insert these into your expression. Then after you insert them into your expression, you can do some manipulation with the squares. You can do manipulation with squares because you've got the square at the top, square at the bottom, and because this was a perfectly symmetrical, you had 2 on the left and 2 on the right, you end up taking squares of both sides. You end up eliminating these volumes, and then you can rearrange it, and you can solve for your x, right? You solve for your x. So this arithmetic I'm not going to go through with you. You can look at it. You can go back, look at it, play with it when the video is posted. And remember what x was. We assigned x to be the amount of I2 that was formed, and so that is how you would arrive at the amount of I2 that is formed. And so at that point, what I'm going to do is I'm going to stop the session here. If you have any questions, you can you're free to ask, and we can take it from there. So I think 5 minutes, we're already on time, so we're supposed to close. But I think maybe 1 question or 2 questions would be fine. Siabonga, is that okay? Do we normally take questions?
Ashwin, yes, yes. They can ask questions.
Okay.
Anyes Kwazi, are you asking a question?
Can you please explain how do we get how do we get the answer of 6.2.2?
In the meantime, can I request you guys, the learners, to make sure that please you don't leave the class without having signed the register there, which is the link is available on our chat box, as well as the link for the feedback, because we would like to know how you are receiving our sessions as well. Please make sure to follow the relevant links, guys.
Okay, sorry, I was muted there. I'm asking, which question are you talking about?
The question 6 from the May-June paper.
Six point two point two. No, I didn't get that answer for anything. That's 0.071. 0.07143, right? So that's the answer here. Not sure if you can see that. That's I think the only numerical answer in this. Yeah, that's your answer. 0.071. Okay, any other questions? Do you have any questions in the chat that are unattended, Nyameka? I'm sure you've been handling that.
No, we don't. We just now they just filling in the register, those who didn't.
Okay. There's also the mailboxes, right? So if you guys have any questions, you can email the mailboxes and then we will get back to you with that. So from here, I think I'll hand over to Siyabonga. Yeah. Siyabonga, you can take it from here.
Yes,
Thank you.
Yes, Ashwin. Thank you so much, Ashwin, for a wonderful session. I think, colleagues, Elenas, I will just play one of the videos here. So if you done, you can log off. You can leave the session if you satisfied with anything at the moment, or if you want, you can also watch the video towards the end, guys. Thank you.
The University of KwaZulu-Natal's College of Agriculture, Engineering and Science is committed to making a difference in our world, from the classroom and laboratory to the field. It provides one of the finest study and research environments on the African continent and is recognized internationally as a center of excellence. Agriculture, Engineering and Science is one of 4 colleges that make up the University of KwaZulu-Natal and is home to over 8,700 students and approximately 700 staff. 3 of the university's 5 campuses form the core of agriculture, engineering and science activities in the region. The college comprises 5 schools: agricultural, earth and environmental sciences, engineering, chemistry and physics, life sciences and mathematics, statistics and computer science. Engineering is offered on the Howard College campus, agriculture on the Pietermaritzburg, and all the other sciences on both the Pietermaritzburg and Westville campuses. Exceptions are agricultural engineering, which is offered in Pietermaritzburg, and geology, which is offered at Westville only. To compete with the best and to meet the challenges of the 21st century, South Africa needs highly skilled professionals in the areas of agriculture, engineering and science. We offer a wide array of interesting and innovative degree programs that open doors to a variety of different careers. Some degrees are unique to UKZN and are not offered at other tertiary institutions. For example, we are the only university in South Africa to offer a fully accredited agricultural engineering degree and one of only 2 universities in the country to offer a BSc in land surveying. Our postgraduate food security training program is the only one in the world, and we have the widest range of agricultural disciplines at any single South African or African campus. The choices of degree and the options on offer may seem confusing at first. Engineering degrees are more specific, and the options are usually career-focused. Emphasis is placed on training in the specific principles which engineers deal with in their professions. Engineering offers 7 different professional specializations. There are also degrees in land surveying or geomatics and property development. In science, there are structured or career-focused degrees. These include fields as varied as chemical technology, marine biology, industrial and applied biotechnology, and computer science and information technology, to mention a few. There are also more general degrees with a lot of flexibility. In this case, students have the choice of studying a BSc M stream in maths, physics, computer science, and statistics. All of these have a strong mathematical component. The other option is a BSc LES stream with a focus on the life and environmental sciences with subjects such as geography, genetics, botany, hydrology, zoology, ecology, and microbiology. In agriculture, there are various different options that involve practical and scientific applications. Students can combine science subjects with specific agricultural disciplines for a 4-year Bachelor of Science in Agriculture degree. These are more career-orientated. Agriculture and agricultural management are 3-year degrees with a higher practical component. Dietetics is a professional qualification that deals with the role nutrition plays in the promotion of health and the treatment of disease. Most degree programs across the college have field trips and projects that contribute significantly to the curriculum. This ensures that students learn in real-life situations under full field conditions. Many of our lecturers have received Excellence in Teaching awards, are recognized internationally, and are rich in practical experience. Students have access to excellent facilities that rank amongst the best in the world. 300 million rands has recently been invested in new teaching and research facilities, state-of-the-art laboratories, and improved equipment. The 30 million rands new School of Engineering building is the envy of engineering campuses across the country. Agricultural students have access to a 356-hectare research and training farm situated near the Pietermaritzburg campus. This facility provides students with hands-on training and is used extensively as an outdoor laboratory for teaching and research in areas such as animal and poultry science, horticultural science, and agricultural engineering. Adjoining Ukulinga is the Bisley Valley Nature Reserve, which supports a diversity of plant and bird species, as well as some large mammals. It provides a rich learning and research environment for staff and students. Based on the Westville campus, the college possesses unique facilities for research into higher voltage power transmission. These facilities are available in only 3 other places in the world and form part of the Eskom-sponsored Science and Technology Innovation Park. The Science and Technology Education Center showcases the college's scientific achievements and promotes the public understanding of science, engineering and technology within the region. The college houses a wide range of sophisticated equipment in its microscopy and microanalysis units, staffed by highly qualified and skilled technical specialists. The College of Agriculture, Engineering and Science prides itself on its graduates who are highly sought after. In a market characterized by a shortage of qualified professionals in science and technology, our graduates are readily employed around the world in the fields of agriculture, science, commerce, industry, engineering and research, to name just a few. Research plays a major role within the college and operates at the cutting edge of technology. The college has the highest research output in the university and produces the most research publications. There are over 60 well-established research groups and centers within the college. The African Center for Crop Improvement caters for students from all over Africa. It is one of only 2 African plant breeding programs on the continent. Based in the School of Agricultural, Earth and Environmental Sciences, the African Center for Food Security focuses on alleviating hunger in Africa. It offers food security training programs, undertakes academic and applied research, and provides policy and program support. Promoting sustainable engineering practice is the Center for Research in Environmental, Coastal and Hydrological Engineering, or CRESH. It deals with the interaction between engineering and the natural environment. The Mechatronics and Robotics Research Group in the School of Engineering provides an excellent research and education environment for its senior undergraduate and postgraduate students. Judged one of the best research centers at the university, the Center for Plant Growth and Development focuses on high-quality research in the plant-based disciplines of plant physiology, plant molecular biology, and ethnobotany. The Center for Quantum Technology deals with physical phenomena at the microscopic level. Quantum physics led to the development of the transistor and the laser and is currently being used to develop quantum computers and quantum cryptography. The college is committed to access and readdressing the disadvantages and inequities of the past. The highly successful Unite Engineering program and the Science Access Foundation and augmented programs offer alternative access to university, equipping students from disadvantaged backgrounds with the skills and knowledge to pursue their degrees of choice. Both these programs contribute significantly to advancing Black African scientists and engineers in South Africa. Staff and students contribute to a number of outreach and community initiatives that focus on social responsibility, sustainable development and upliftment of the wider community. The college also engages in activities involving the pursuit and understanding of science, engineering and technology through exhibitions, festivals and roadshows that target high school learners and the general public. The college has minimum entry requirements for its programs. These differ from degree to degree, but all require a national senior certificate and minimum performance levels in mathematics and either physical or life or agricultural sciences. For those who do not meet the minimum requirements, access programs are available. Additional information and brochures can be obtained from the contact information accompanying this video. The College of Agriculture, Engineering and Science is proud of its contribution to the university, the region and the country.
UKZN is one of the best. I definitely understand it's one of the best in South Africa. So for me, there was no other institute that I would have preferred other than UKZN.
We have the best facilities here in terms of laboratories, in terms of equipment, in terms of human resources, in terms of literature.
UKZN is one of the best universities in the country that teach agriculture or natural sciences.
What I think is good about this college is the level of international collaboration that we have. We have friendships with universities all over the world, which means that we're keeping up to a great international standard.
UKZN has got much more facilities and it's recommended worldwide to do your science studies here. Life begins here. Yes.
We continually strive to be academically excellent, innovative in research, and critically engaged with society. We invite you to join us or work with us to be part of this exciting team.
Bye-bye, guys.